Chapter 7, Lesson 6 of Advanced Algebra. Now that we've looked at adding, subtracting, multiplying, and dividing functions, we want to take a couple of videos and discuss domain and range, not only of the original functions, the ones that we're adding, subtracting, multiplying, or dividing, but then also taking a look at the domain of the resulting function. And is the domain of the resulting function related in any way to the domains and ranges of the original functions? So let's begin by talking about domain. Now, the domain of a function is the set of all the possible inputs of the function. In other words, we're looking at the different values for which we can substitute in for x. Now, we're going to begin with the assumption that we can use all real numbers. We're going to assume that we can use any number we want: positive, negative, fraction, not fraction, rational, irrational, and then we're going to look for mathematical impossibilities created by substituting in any of those real numbers. So we begin with the largest set possible, and then we look for, are there going to be any mathematical impossibilities created by using certain x values. The range of a function is all the possible outputs. Once we know the types of values that we're going to be putting into the function, then what kind of functions, or what kind of values, are we going to be getting out of the function? Are we going to be getting just whole numbers out? Are we just getting positive numbers out, just negatives? What are the types of y values that are going to be produced from these x values that we're substituting into the machine, or into the function? Functions are very much like machines in that there's certain things and certain types of money that you can put in, but you can't put in anything. So we would begin, for example, in the United States, we'll begin by assuming, okay, we can put all kinds of American currency into the machine, and then we would look to eliminate any types that you can't use. So for instance, maybe you can't use pennies in this machine, so you would use all American currency except pennies. Maybe the portion of the machine that accepts dollar bills maybe can't handle any kind of denomination over 20. So again, that's going to limit our domain even more. So we would begin by, well, we can use any kind of American money we want, except you can't use pennies and you can't use denominations over 20. So we begin by assuming the largest set, and then we eliminate the ones that we can't use. And then for the range, we pretty much do the same thing. So the range, this is let's say a food machine or a drink machine. We'll assume that you can get any drink you want out of this machine, and then we'll start eliminating those that you actually cannot get out. So maybe you can't get out Pepsi products, you can't get out dairy products, but anything else you could get. So you can get any drink you want out of this machine, except you can't get Pepsi and you can't get dairy products. So that would be the range, everything except those products. And functions are very much the same. They're machines. You put an x value in and you get a single y value out. So let's look at how we can then now determine what these domain values are. When you're drawing your coordinate plane, your xy axis, you have your y-axis and then you have your x-axis. When you draw your x-axis, what you're actually doing is you're drawing a graphical representation of the domain, all real numbers. That line represents all real numbers, all the positive ones, all the negative ones, all the fractions, all the integers, all the irrational, all the rational. So when you draw that one line, that's what you're actually drawing. You're drawing all real numbers. And then we'll go along this number line and we pick different numbers and we substitute them into the function. So we begin by assuming that we can use any of these x values that we want. We then look for and we'll exclude any of the x values that, if we substituted that x value into the function, because of the mathematical properties of the function, it would create a mathematical impossibility. Well, what are those mathematical impossibilities that we have to look for? And there are only two of them. So what we want to look for are these. Does the mathematical property of the function create a possibility where I would be dividing by 0 if I substituted in certain x values? Because division by 0 is not possible, or it's undefined, I cannot use any x values from these real numbers, which, if I put that number into the function, would create a 0 in the denominator. So if there's any denominator with a variable in it, I'm going to have to determine, well, what's the x value that I can't use, because if I did use it, it would make that denominator 0. The second impossibility I got to look for is a negative radicand. You remember that we cannot take square roots or fourth roots or sixth roots or even index roots of negative radicands. So from these real numbers, I cannot substitute into the expression any x value that's going to create a negative radicand. So I'm going to have to exclude those from my domain. Okay, so when you look at a function, you're looking for two things. Is there a division portion to the function? And if there is there a variable in the denominator? Then I'm going to have to determine what value for that variable would make that denominator 0 and exclude that from my domain. And the second thing I'm going to look for then, is there a radical sign with an even index in my function? If there is, I'm going to have to determine if there's a variable in that radicand, which value of x by putting it in would create a negative radicand, thus creating a mathematical impossibility. Alright, so that's what we're looking for. Now, hands-on applicationally, what does it look like? So, looking at the first restriction is division by 0. So if I look at a function, and the function has a variable in the denominator, that variable in the denominator is going to create a restriction to the values that I can use out of the real numbers. Any value that I would choose to substitute in for the x value that would make it 0 cannot be in the domain. So to determine what this is going to be, all I have to do is take the entire denominator of what I'm looking at, write a little equation, or actually a non-equation, I don't know if it's a non-equation, a non-equal equation for 0, and then solve it, and then write my domain using set notation. Okay, so for example, as I look at this first example, I notice that this is a division problem and it has a variable in my denominator. Now I know that I can never have the denominator be 0, so I'm going to take what I know, the denominator cannot be 0, and I'm going to simply substitute in the denominator. So I know the denominator cannot be 0, so what's my denominator? 3x plus 5. So I know 3x plus 5 cannot be 0, and now I solve this like I would an equation. So I'm going to subtract 5 from both sides and divide by 3. So my denominator, if I were to use the value negative 5/3 in for x, that would create a 0. It would make the denominator 0, so that's not part of my domain. So to write my domain for this function, I begin with all real numbers such that, this little line means such that, or as long as x is not negative 5/3. Okay, so this is called set notation. This is the notation for real numbers. This line means such that, or as long as, and then we have the restriction listed here. Okay, so 3 parts to the set notation. Well, then I use my braces, so 4 part. Using braces for the outside, I begin with all real numbers such that, or as long as, and then I write what my restriction is here. And again, for the denominator, I simply say the denominator cannot be 0. For the second one here, I want you to take a look at that. This is very interesting. X squared. It's in my denominator, and I can write x squared, the denominator, cannot be 0, and I solve. Taking the square root, x cannot be the square root of 0 or 0. So my domain for this function is all real numbers such that, or as long as, x is not 0. Okay, so this would be my domain, and sometimes we put this domain using the letter D. Alright, one more example here, and I think you got this. 1 over 2x plus 3. Variable in the denominator. My denominator, 2x plus 3, cannot be 0. and then I solve the equation. 2x cannot be negative 3, x cannot be negative 3 halves. So my domain for this function is all real numbers. We begin with that, such that, or as long as x is not or does not equal negative 3 halves, so this would be my domain for the function. So in order to determine the domain when you have division, it's very simple. You just put the denominator cannot be 0, you write that equation, and then you simply solve it for x. Now the second thing we need to recognize is if we're going to have a negative radicand. That's the other mathematical situation that will create a domain restriction. A variable in the radicand is going to create a restriction to values in the domain, because any x value, again, that I would substitute into the expression that would create a negative radicand cannot be used. So again, we're going to take what we understand, and that is this. The radicand cannot be negative, so it cannot be less than 0. So we're going to simply write that as an expression, an inequality, and then solve it, and then write it in set notation, the domain. In other words, we're going to say the radicand must be greater than or equal to 0. So as I look at these, again, if I have a square root, then I know this radicand, I know that the radicand must be greater than or equal to 0. So I'm going to simply substitute in the radicand for the word radicand. So x minus 7 must be greater than or equal to 0, and then simply solve this inequality. So x must be greater than or equal to 7. And then I'm going to use domain or set notation again. I'm going to begin with all real numbers such that, or as long as, x is greater than or equal to 7. And so this would be my domain. So we're going to simply take the radicand and set it greater than or equal to 0, because that's what it has to be, greater than or equal to 0. Here we have x plus 3. I know that this radicand must be greater than or equal to 0, so I'm going to write that out, what I know. The radicand must be greater than or equal to 0. I'm going to solve it. So my domain then is going to be all real numbers as long as, or such that, x is greater than or equal to negative 3. Alright, and then for this last one, take note of this. If you don't remember, there's something that happens here that you have to remember. Again, we simply have a radicand. The radicand negative x minus 4 must be greater than or equal to 0. So if we move the negative 4 over, that becomes 4. Now here's a little rule you have to remember. When you divide by a negative, you have to reverse the sign of the inequality. So x must be less than negative 4. So my domain for this expression is going to be all real numbers as long as the x values that are used are less than or equal to negative 4. Okay? So as a quick review then for domain, there's two situations we have to look for, division by 0 and a negative radicand. If any of those are part of the function, then I simply determine what the x values are that would make that division by 0 or negative radicand, and then write my domain using set notation.